Okay. Well, yeah, it's really, sort of a pleasure to be here. I'm happy to be able to talk to you all. I mean, from such a distance. Yeah, this is sort of really interesting. I gave a talk in like Brazil a couple weeks ago, and it's well, I feel like I'm everywhere while not actually leaving anywhere. But yeah, thank you for having me. I really appreciate it. Okay, so what I want to talk about today is some work that I've done, or I sort of have finished-ish over the last little while. So really what I want to do is I want to talk about these log symplectic pairs and how, the relationship to, mixed Hodge structures and their geometry and things like this. So I should explain what I'm talking about first of all. So the motivation, not necessarily the motivation for me, but maybe one of the better pieces of motivation for talking about all this is degenerations of hyperkaehler varieties. So before I'll talk about that, I'll talk a little bit about the degeneration of K3 surfaces, because this is certainly something that starts off the story for me. Okay, so semi-stable degeneration, just to give the basic definition of a degeneration, this is a proper flat surjective morphism to the unit disk whose fibers away from zero are smooth and whose fiber at zero is normal crossings. We also want that that pi vanishes to order 1 exactly along each component. So that is, there's no multiplicity to the components of our degeneration. So this should be a fairly, easy to understand definition. I'm sure you've all seen it before. And so generally speaking, these things are fairly well understood, specifically for curves and surfaces. And in particular, for K3 surfaces, these things. So these are well understood for K3 surfaces, and the classification sort of goes as follows. So there's this theorem going back to Kulikov and Persson and Pinkham, which says that if you have a semi-stable degeneration of K3 surfaces, so that the fibers, the smooth fibers are K3s, I mean, so that's degeneration of K3 surfaces, and so that all the components of the central fiber are Kähler. And so finally, that the canonical bundle of this S, or there shouldn't be an S prime, but S is equal to 0. So it's a trivial canonical bundle. So this is some sort of relative minimality condition. Then the fiber over 0 takes one of the following 3 forms. So you can have a type 1 degeneration of K3 surfaces, which is not really degeneration, it's just a K3 surface. You can have a type 2 degeneration of K3 surfaces. So this is going to be a chain of surfaces which meet along elliptic curves, so smooth elliptic curves. So for instance, you can take the degeneration of a quartic hypersurface in P3 to a union of a cubic and a plane. So if you just take this thing as a pencil of quartics, this thing will be singular. If you resolve these singularities, you'll get a type 2 degeneration of K3 surfaces. And the type 3, the third type, is when you have the central fiber being a union of rational surfaces whose dual intersection complex is a triangulation of the two-sphere. So for example, I mean, the standard example is you take a pencil of quartics going to the 4 coordinate hyperplanes in P3. So just taking the corresponding pencil, you'll get a singular space again, and resolving these things will give you a type 3 degeneration of K3 surfaces. Okay. So this is old and familiar, but I want to go a bit into like the characteristics of this because these are the types of things that I'm interested in understanding generalizations of. So let's think. I mean, so we can distinguish the types of degenerations by looking at how monodromy behaves on the cohomology of the smooth fiber. So if you let ST be a smooth fiber of pi, so we can distinguish the types of degenerations by looking at the monodromy. So according to Clemens and Landman, and I think sometimes Grothendieck's involved in this, for a semi-stable degeneration, the monodromy action on cohomology should be unipotent. So we can take its log. So this is this n guy here. So if you take any degeneration of K3 surfaces, or sort of a semi-stable degeneration of K3 surfaces, we can distinguish the type by the action of monodromy, or the action of the log of monodromy. So in type 1, of course, your monodromy is just trivial, so n is equal to 0. In type 2, you have this condition that n squared is equal to 0, but n is not equal to 0. So you can think about this in terms of the sizes of Jordan blocks. So in this case, the size of the Jordan block is at most 2, I suppose. And in type 3, the thing that you'd sort of expect happens, you go up by 1. So n cubed is equal to 0, but sorry, this should say squared, n squared is not equal to 0. Okay, so you can distinguish these things by monodromy, and so monodromy feeds into mixed Hodge structures. So you can also say what this means in terms of the limit mixed Hodge structure associated to the degeneration. So maybe I'll say a little word about mixed Hodge structures. So the limit mixed Hodge structure associated to a degeneration. Maybe I should have actually written this in a slide. So this is a mixed Hodge structure. So that is a triple composed of a vector space, a rational vector space. So in this case, this H2S infinity that I'm writing down here, this is identified with H2ST. So the cohomology of a smooth fiber of the degeneration. So you then have two filtrations on this. You have the Hodge filtration. So there's going to be a Hodge filtration on. Essentially, what you do is you take the limit of the Hodge filtrations as you move towards the degenerate fiber. So for a given fiber, of course, there's a pure Hodge structure on the cohomology of that fiber. As you move towards the degenerate fiber, you get you can define a limit Hodge filtration, but it's no longer going to give you a pure Hodge structure. But when you equip it with the monodromy weight filtration, so that is a filtration defined by this N fellow here, then you get what's called a mixed Hodge structure. So that's an increasing weight filtration on the rational vector space, and a decreasing Hodge filtration on the tensor product of this thing with C, and these interact in a nice way so that the weight graded pieces admit a pure Hodge structure of a specific weight. Okay, so you can look at the limit mixed Hodge structure of degenerations of K3 surfaces, and they split again into 3 types, which are pretty easy to distinguish. So in type 1, as I said, it's just the cohomology of the smooth fiber, because you can essentially replace it with a smooth K3 surface. In type 2, it's a little bit more complicated in H2. So you see that the first and third weight graded piece look like the cohomology of an elliptic curve. So if you go back to the geometry, you can sort of see that this is the cohomology of the elliptic curve that the components meet in. Okay, and you can also look at the second weight graded piece, and this is equal to Q to the 18. So when I write Q here for mixed Hodge structure, this just means the Tate Hodge structure itself. So Q to the 18. So this means the unique weight 2. Or sorry, the unique Hodge structure of weight 2, whose H11 is equal to 18, and whose all whose other Hodge numbers are 0. Okay, so that's description of type 2, and in type 3, it's sort of similar. I mean, of course, there's always this symmetry between different weights in the mixed Hodge structures, the limit mixed Hodge structure. So you have the 0th weight graded piece and the 4th weight graded piece just Q, and the second weight graded piece is Q to the 20th power. Okay, great. So that's distinguishing features in terms of maybe the cohomology. We can talk a little bit more about the geometry. So if we go back a couple slides, I mean, it's not worth it, but if you go back a couple slides, you can see that the central fiber, as I said, this is composed of different types of surfaces. And so what you can do is you can build pairs out of these surfaces. So you can take the components of the central fiber, and you can take the intersection between these components and the singular locus of the central fiber. And these will give you a pair consisting of a variety, so a smooth variety, and a divisor. So this is going to be an SNC pair. And such a pair is log Calabi-Yau. So for us, or for me at least, this is just a pair, so that the divisor is simple normal crossings and anti-canonical. Or maybe just normal crossings if you want that. Okay, so geometrically, these again split into 3 types. So there's smooth K3 surfaces, okay, boring. In type 2, there's 2 different things. You get smooth rational surfaces with the smooth anti-canonical elliptic curve. So this is like P2 and a smooth elliptic curve, smooth cubic. And then there's the ruled surfaces over an elliptic curve with the pair of sections giving you your anti-canonical divisor. So in type 2, for type 2 degenerations, you have I said these degenerations are chains of surfaces meeting in elliptic curves. So the stuff at the end, these things are rational surfaces with smooth anticanonical elliptic curves as the intersection with the next components. And the things in the middle are ruled surfaces over elliptic curves meeting in the sections. Okay, and in type 3, as I said, these are rational surfaces. The components are all rational surfaces, and the boundary divisor that you get is just an anticanonical cycle of curves. Okay, so these things can be classified. I think generally speaking, there's a classification in all types. So for smooth rational surfaces, with the smooth anticanonical, this goes back to Friedman and Miranda. So you basically take some sort of basic pair, so P2 or Fn plus a smooth anticanonical, and you start to blow up points in the anticanonical, and eventually you'll get to where you want to go. Similar things happen for ruled surfaces over elliptic curves. You just take, your projective bundle, so a split projective bundle over your elliptic curve, and you blow up points in one of the two sections. And in type 3, so this is something that was described by Gross-Hacking and Kiel, which is you blow up, you take a toric variety, so a toric surface may be smooth, and you take points inside of the toric boundary divisor. So delta, I guess, here is a polygon. So we associate to this a toric variety and a toric boundary divisor d delta. So you take this toric variety and you start to blow up points in smooth points in the boundary, and eventually you get to any type 3 surface in this description here. Okay, so just to summarize, we can classify the components of degenerations of K3 surfaces, and they're all sort of built out of simple things. Finally, I'm going to put down like some description of the mixed Hodge structure on the cohomology of these things. So if you take them as a pair, I mean, when I talk about cohomology of a pair, there's probably at least 2 or 3 different ways to talk about these cohomology groups, and they're all going to be essentially equivalent. So I can take the cohomology of the complement, or I can take the relative cohomology, or I can take the compactly supported cohomology of the complement, and these are all going to be essentially the same. So I'm not going to really distinguish, but I'll describe it in the case of the complement of the divisor. So for a smooth rational surface with a smooth anticanonical, this sort of looks like the mixed Hodge structure of a type 2 degeneration. So you have, some Q sitting in H2 in weight 2, and then you have the cohomology of an elliptic curve sitting in weight 3. Similar things happen for a ruled surface over an elliptic curve. You have the cohomology of an elliptic curve, Y, sitting in weight 2, and you have something else sitting in weight 3, and something else sitting in weight 2. And then just to distinguish these two, H3 is different. And so the last thing is just to say, what the cohomology of a pair consisting of a smooth rational surface and a nodal anticanonical divisor looks like. And so this is, this looks a lot sort of like half of the cohomology of a type 3 degeneration of K3 surfaces. So you have something sitting in weight 2 that is just Hodge-Tate, so it's Q to the something. And then something in weight 4 that is just Q, and everything else vanishes above that. Okay, so these are a lot of the features that I want to generalize, which is why I've sort of brought them up here. So let's start to talk about how these things generalize in higher dimensions. So when I say generalize to higher dimensions, the type of generalization that I'm interested in is generalization that goes from K3 surfaces to hyperkaehler varieties. So there's a similar type of trichotomy on the level of mixed Hodge structures, and this is again, based on just looking at how H2 degenerates. So I mean, one of the sort of, how should I say this? The basic ideas going back at least probably earlier, but at least to Verbitsky, probably earlier, is that if you want to study the cohomology of a hyperkaehler variety, most of that stuff is going to be determined by what happens in H2. So describing H2 of the degeneration of a hyperkaehler variety should give you enough information to talk about the rest. Okay, so so let's take a semi-stable degeneration of hyperkaehler manifolds. So this is some sort of metric condition. This at least means it's I'll come back to talking a bit more about symplectic stuff and hyperkaehler stuff later, but I'll sort of take it as given that people know what this means. which is probably reasonable. I've been teaching a lot of calculus recently. I'm probably over-explaining things. I apologize if I'm doing that. Okay, so you can take the following types. You get the following types of limit mixed Hodge structures, depending on the types of degenerations. So in type 1, so if your monodromy action on H2 is trivial, so the monodromy breaks up the same way as it did in the K3 case. The action of the log of monodromy, like the structure is exactly the same. So that's what I'm referring to with these types here. So in type 1, the limit mixed Hodge structure is always just going to be pure. In type 2, you get exactly the same breakup as before, except you just don't know what the thing in the middle is, what the second weight graded piece looks like. And in type 3, you again get the same type of structure as before. So why do you get this? This is just some statement about how Hodge structures can degenerate. Weight 2 Hodge structures with H20 equals 1. This is how they degenerate. Okay, so this is just very broad classification type stuff. But if you want to say something specific, there's this work of Collard, Laza, Saka, and Voisin, which tells you how this cohomological degeneration criteria here relates to actual geometry. So if you take a degeneration of hyperkaehler varieties so that it's minimal, so this means that the canonical bundle on this whole thing is going to be trivial. And so it's DLT, which, to be honest, I have a hard time explaining. So this is some condition that's weaker than my semi-stability condition because it allows singularities and different types of components. So in type 1, so if I have such a degeneration, and if I have a limit mixed Hodge structure of the first type, then after base change, the central fiber can be made smooth. So this is, what I'm talking about here is some sort of partial generalization of this theorem of Kulakov, Person, and Pinkham that I described before. So in type 1, you can make it smooth after base change. And in types 2 and 3, you can do something not quite as nice as what we saw before, but we can also give, some sort of geometric classification of what happens at the central fiber. So what they get is some sort of statement about geometry. So it's a statement about the dimension of the dual intersection complex of these things. So these dual intersection complexes, if I recall correctly, they're at the very least pseudo-manifolds, if not manifolds. So you can talk about their dimension. So in type 2, the dimension is the dimension of the fiber divided by 2. And in type 3, the dimension of the dual intersection complex of the central fiber is the dimension of the fiber. And so moreover, actually, in type 3, I think what you get is you get a homology Pn, where n is the dimension. Okay, so this is their work. So what do I want to do now? So this is sort of all just background. What I want to talk about now is a bit more sort of forward thinking. So what I want to do is I want to study the geometry of the components of central fibers of degenerations of hyperkaehler manifolds. So this is like broadly speaking my motivation for looking at this. So why would you do this? I mean, one possible far future type of goal is to try to address the problem of constructing new hyperkaehler varieties. So, I mean, one thing that is known is that if you have something that looks like a degeneration of hyperkaehler varieties and it's log smooth, then you can smooth it. So this is work of I think this was a PhD student of I forget who. But the idea is that if you have a log smooth degenerate variety, then you can smooth this. So this is a generalization of work of Kawamata and Namakawa from back in the 90s. But also, I mean, on the other hand, you can also think about what we get out of this as being interesting in their own right. These are things that look a lot like cluster varieties, and as you'll see later, sort of things like character varieties start to enter the picture once you start to study these things, or stuff like cluster varieties. Sorry. Okay, so that's probably the main goal, which will take up probably most of the rest of the talk. But the real interesting thing for me is to study the cohomology rings of such things. So what we'll end up getting is things that look like maybe mixed analogs of structural results about cohomology of hyperkaehler varieties. So Verbitsky did some very nice work about the cohomology of hyperkaehler varieties back in the 90s as well. So what we'll get out of this is some sort of understanding about how cohomology rings of what I'll call log symplectic pairs work. And so the study of the cohomology rings of these things can also be extended to studying the structure of cohomology rings of limit mixed Hodge structures of degenerations of hyperkaehler varieties. So this will provide, a new proof of a result of Solbatenkov. And I'll explain a bit of this later. This also gives some idea of how to approach things like Nagai's conjecture in a sort of abstract way. Okay, so this is sort of the plan from here on out. This is the idea. Okay, so let's. I guess I'll get started on all of this. Okay, so what do I want to study? So the things that I want to study are things that are called log symplectic pairs. So you'll take a variety, and for me, I'll take a simple normal crossings, or at least normal crossings divisor y. So this thing will be called log symplectic if there is some holomorphic log 2 form, so log 2 form on x with poles along y, so that if I take the highest possible power of the sigma of d, this is going to be non-vanishing as a section of the log canonical bundle. Okay, so I mean this implies log Calabi-Yau, but of course it's stronger, right? Just in the same way, hyperkaehler implies Calabi-Yau, but it's a much stronger condition. Okay, so I mean, just a comment, this is essentially given here, but I mean, the definition depends on the fact that your dimension is even, so it's good to keep in mind. What are some examples? So basic examples, going back to what I talked about already, is if you take a pair consisting of, say, a surface and a simple normal crossings anti-canonical divisor, then this is immediately log symplectic, just sort of the same way that in dimension 2, being Calabi-Yau is the same thing as being a symplectic variety or holomorphic symplectic. If your boundary divisor is empty, then this is just called a holomorphic symplectic variety, and so hyperkaehler varieties are an example of holomorphic symplectic varieties. So it's a much more stringent condition than just being holomorphic symplectic, but it is an example. So examples of these include so SN. So this means the Hilbert scheme of n points in a K3 surface, and there's the generalized Kummer varieties. So these are examples that go back to Beauville. So I mean, I won't say too much about that here. And so another class of examples, we'll see more later, but here's just sort of basic ones that you can sort of extract from the literature, is an example of Ran, where he basically takes a Hilbert scheme of points on a surface with a smooth anti-canonical divisor. So using the smooth anti-canonical divisor on the surface that you start with, you can build a divisor on the Hilbert scheme of points, which is smooth. The divisor that you get, so this pair, the pair consisting of this Hilbert scheme of points on a rational surface or something with the divisor, so this is log symplectic if you forget about the SNC condition here. But what Ran really does is he gives a resolution of this divisor, which produces an SNC pair, which sort of remains symplectic. So this is a bit of work to do. So these are just examples that sort of come from the literature. Okay, so great. So as I was saying, my motivation for all this is, to at least start or to sort of talk about degenerations of hyperkaehler varieties. So I want to say that, other examples of log symplectic pairs come from components of degenerations of hyperkaehler varieties. So that's the goal at this point. So I want to be a little bit more strict about the type of degenerations that I look at in order to get nice components. So let's see. So a good degeneration. So this is a semi-stable degeneration, so that there's an element sigma. So this is sort of mirroring the definition I gave before. So this is now a relative log 2 form on the fibers of the map, which I probably should call pi. That can have log poles on the fiber over 0. Okay, and so again, I require non-degeneracy. So this is a vector bundle, this logarithmic bundle here, so I can certainly take its highest wedge power. And so the non-degeneracy condition is essentially the fact that the highest wedge power doesn't vanish. So an immediate observation here is that the fibers, the smooth fibers of this thing, are themselves holomorphic symplectic. So there's a holomorphic symplectic form there. Right, okay, so this is this comment. And so a less immediate observation, which is still not extremely difficult to prove, is that if you have a component of the central fiber of a good degeneration, and you take y to be the intersection between that component and the singular locus of the fiber over 0, then this pair is again a log symplectic pair. So this is, what I'm saying here is that this is another source of examples of log symplectic pairs. It's these good degenerations of homomorphic symplectic varieties. Okay, great. So how does one prove this? It's essentially just a straightforward proof. I mean, I won't say much about this, but the proof is really straightforward, which is why it's called a proposition and not a theorem. It's essentially you just take the symplectic form, the sigma here, on your good degeneration. You take the wedge with d log pi, and then you take the residue on each component, and then it's sort of a local check to see that what you get is non-degenerate. Okay, so that's relatively easy. But I should also mention before moving on that this whole good degeneration condition is a little bit of a fantasy, to be honest. In dimension 2, it makes sense to talk about these things because these essentially just mean talking about these nice models of K3 degenerations that I was talking about earlier. So these are well understood and they exist, and you can say a lot of stuff about this. In higher dimensions, I only know of one example of good degenerations, and this was something that was done by Nagai in dimension 4. So essentially what he did was he took a type 2 degeneration of K3 surfaces and took the and sort of produced a degeneration of the corresponding Hilbert schemes of points of pairs of points. So this gives an example in dimension 4. I should also mention that this definition is also due to Nagai. This is not out of nowhere. This is sort of him producing an example of what he defined. Okay, so take this with a little grain of salt, but this is another source of examples. I mean, you can be a little looser with this, but this is sort of the theorem. Okay, so then you ask yourself, is this it? Do we just look at log symplectic pairs? I mean, is there something more to look at when we want to think about the components of degenerations? As I said before, holomorphic symplectic is implied by hyperkaehler, but hyperkaehler is a stronger condition. So if I want to look at the degenerations of hyperkaehler varieties, I can ask if there are any extra restrictions that are placed on the components. So that's what I want to address now. So I want to address this in terms of mixed Hodge theory. So going back to the title of the talk, I'll introduce some sort of technological gadget here. This is not extremely important to understand, but what you can do is for any mixed Hodge structure, you can produce this functorial decomposition. So again, V is a rational vector space. F is a decreasing filtration on V tensored C, and W is your increasing weight filtration. So sort of analogous to how you break up a pure Hodge structure into HPQ pieces, you can break up any mixed Hodge structure into IPQ pieces. So as I said, this is functorial, but this is not like in any way canonical. So you can always do this. And so this gives a nice way to sort of study these things. So if I have a log symplectic pair, I want to define some sort of condition on sigma that means that the mixed Hodge structure behaves nicely with respect to sigma. So this is this definition of pure weight. So I say it has pure weight W if the corresponding element in H2 of X is contained in I2W. So I'll say a little bit about this definition. So sigma is, of course, a log form with poles along y, so it'll give you a holomorphic form on x without y, so the complement of y. So by, this goes back to Deligne, that such a form is going to be closed on the complement of y. Therefore, it'll give you a class inside of H2. So a priori, this class, the class of sigma, lives inside of the direct sum of three of these I2, the direct sum of I20, I21, and I22. So saying that this has pure weight means that not only is it in the direct sum, but it's actually in one specific piece here. So that's this sort of purity condition, that is sort of, instead of splitting as a bunch of things, it is in exactly one thing. Okay, so this is our basic definition. And so the theorem, which is surprisingly difficult to prove compared to how easy the corresponding statement about log symplecticness was to prove, is that if you have a good degeneration of hyperkaehler manifolds, and if you take an irreducible component of the fiber over 0, then this pair itself is log symplectic of pure weight. So this is some sort of Hodge theoretic extension of the previous proposition, which says that these are distinguished in terms of their mixed Hodge structures. So you can, so as I said, so there's there are these types to degenerations of hyperkaehler varieties. So, and then there's this variable W, the pure weight. So how do these relate to one another? Well, pure weight 0 corresponds to type 1, pure weight 1 corresponds to type 2, and pure weight 2 corresponds to type 3. Okay, right. I mean, so just, yeah, okay, so there's not much to say here. This is just the correspondence. Okay, so so this is some sort of abstract cohomological condition, something about mixed Hodge structures, blah, blah, blah. In terms of geometry, you can also see what this means. So you can figure out how to interpret the pure weight condition in terms of the pair xy. So if you have pure weight 0, if you have some log symplectic form of pure weight 0, then you can show that the boundary divisor is empty. So this corresponds to the fact in the Calabi-Yau theorem, if you have a degeneration of type 1, you can always make this smooth. If you have a log symplectic pair whose log symplectic form is of pure weight 1, then the dimension of the dual intersection complex is the dimension of x divided by 2 minus 1. Again, this corresponds to this statement in the Calabi-Yau paper that says, if you have a degeneration of type 1, then the dual intersection of the central fiber has a specific dimension. And similarly, for type 2, you can determine the dimension of the dual intersection complex in terms of the pure weight as well. So this is, again, corresponding to the KLSV theorem. Okay, so one consequence of this maybe is that having a log symplectic form of a given pure weight, having one log symplectic form of a given pure weight means that every other log symplectic form of pure weight on that variety will have the same weight, right? If you have a log symplectic form of pure weight 0 on your variety, then if you choose another one, it can't be another one of these weights because that would change the dimension of the dual intersection complex. Okay. And another consequence of this is that this sort of recovers this theorem of KLSV, but what I'm getting is a much, much weaker version because I have to assume that you have a semi-stable degeneration instead of just DLT. So this is a much weaker version, but some of what they did can be recovered. Okay, another consequence is that this will actually give you criteria for when something cannot be a component of a degeneration of a hyperkaehler variety. So for instance, I have this example here. So if you have a K3 surface and a pair consisting of a smooth rational surface and a smooth elliptic curve, taking the product of these things as pairs is log symplectic, but it no longer has a symplectic form of any sort of pure weight. So this can't be a component of a degeneration of hyperkaehler varieties. Okay. So this is sort of your main motivating idea. Why should we study these things? Well, one reason to study them is that these are the components of degenerations of hyperkaehler varieties. Okay, so let's produce some more examples. So the most basic example of a log symplectic pair of pure weight is what you get by taking a smooth torque variety of dimension 2D. So if you take the big torus inside of this torque variety, you can produce log forms or forms on any torque variety with log poles on the torque boundary, just by essentially choosing a form on the torus, so that these alpha ij's, so that these are just complex numbers. So if you choose this so that the corresponding form alpha ij, so that this is non-degenerate, this pair or this form omega will be a log symplectic form of pure weight too. Okay, good. So very easy, toric example shows up everywhere. So another type of examples which comes from, I guess technically this starts in work of Fagan and Odesky, but it was more worked out in the work of Gualtieri and Pym, and more precisely worked out in Pym's thesis. Is that if you take a smooth elliptic curve, you can embed this inside of P4 by taking a degree 5 line bundle and then taking the corresponding map. So if you have such an embedding, you can look at the secant variety of this embedded elliptic curve. So this is, of course, just taking pairs of points on the embedded elliptic curve and taking the P1 that connects them and taking the closure of the union of all these. So this secant variety is a quintic hypersurface, but it's going to be singular along a subvariety which is biregular to the symmetric square of the corresponding elliptic curve. Okay, so this is now, so if you just look at this thing as a pair, this P4 and this variety secant of E, this thing is log symplectic, but it is not log symplectic with simple number crossings divisor, since its singularities are, the singularities are pretty bad. So what you have to do is you have to blow up the singular locus. So if you blow up P4 in V, this will resolve singularities of the secant variety. But the price you pay is you add another exceptional divisor. And if you take the pair consisting of this blow up along with the divisor consisting of the proper transform of secant variety of E and the exceptional divisor, the corresponding pair that you have is log symplectic of pure weight 1. So you sort of start to see that, like in pure weight 1, there's always going to be an elliptic curve or something like an elliptic curve floating around. This is kind of the philosophy here. Okay, good. This is my example. So these are two examples. How can we produce more is sort of the question that I want to ask now. And the answer is, of course, yes. So how do we produce more examples from old examples? So a log symplectic variety is also has the structure of a Poisson variety. So you get a Poisson structure on X. So you can look at the symplectic leaves of this Poisson structure. So this is places or maximal subvarieties where the Poisson structure gives a symplectic structure. So there's, of course, the big open leaf in this variety, which is the open subset X without Y. So then the log symplectic form just becomes a symplectic form. If you take the complement, there's no log poles to worry about. You can also find symplectic leaves in the components of the boundary divisor. And these can be detected in the following way. So you take your symplectic form sigma, and you take its residue along the boundary divisor Y. Then you look at the subvarieties along which this symplectic form, or this residue of a symplectic form, is equal to 0. So this will give you some sort of foliation, and these things are leaves of your Poisson structure. So the theorem is that by using leaves of this Poisson structure, you can produce new log symplectic pairs. Okay, so the theorem goes as follows. So if you have a log symplectic pair, and you have a symplectic form of pure weight W, so log symplectic form. So take Z to be, or I can say Z, so take Z to be the smooth closure of a smooth symplectic leaf of this, of codimension 2, so something that was described in the previous paragraph. So assume that it's contained in a component of Y, and so that it intersects the singular locus of Y transversely. So this is some sort of genericity condition on the leaves that you're taking. So then take the blow up along this thing. So blow up X along this leaf that lives inside of the divisor. and take the proper transform of the original boundary divisor as your boundary divisor in this pair, and take as your total space the blowup. So then this pair here is log symplectic, and the form that you get by pulling back sigma, the original form, this is a pure weight W. Okay, so this should be reminiscent of things that we saw before. So when we were talking about the classification of log symplectic surfaces, what we did was we had sort of these basic pairs consisting of some surface and an anticanonical divisor, and what we did to produce the rest of them was we just blew up points inside of the anticanonical divisor. So I mean, these log Calabi-Yau surfaces are log symplectic, and if you look at what happens with, these Poisson, these symplectic leaves in the dimension 2 case in the boundary divisor, the ones that you find here, these are just points. So in fact, this is some sort of generalization of that statement. So you can produce new log symplectic surfaces by blowing up points in the boundary, and in order to do this with log symplectic pairs of arbitrary dimension, you just blow up the symplectic leaves in the boundary. Actually, I should ask, when should I stop? Should I leave 10? What's my boundary here?
Oh, don't worry about it. I mean, honestly.
Oh, okay. I mean, I can continue for a long time. I have more.
Well, I'd have to go, but that's okay.
Okay, so maybe I'll shoot to finish by 10:55 if that's all right.
Yeah, that sounds good.
Okay, great.
Yeah.
Okay, so here's the theorem. So you can produce many new examples from old examples. This is sort of the idea, and so we can try to look at what happens when you try to produce when you try to run this for the two examples that we saw before. So let's take the toric variety that we started with. So you take the log symplectic form omega, which corresponds, if you think about this, this will correspond directly to a non-degenerate alternate pairing on the lattice M, so the lattice in which the fan lives. So if you take a toric boundary divisor, this will correspond to a ray in the fan sigma. So this will give you a primitive element of M, the primitive generator of this ray, primitive rational generator. So therefore, what you get is some element in the lattice N by taking alpha with rho, so your ray generator in the previous sentence, in N. So this will give you a monomial function on the big torus inside of X sigma. And I apologize if I mixed up my M's and N's at some point here. Okay, so you have this. So I want to use this to describe symplectic leaves. So what you can do is you can just take the fibers of this monomial function and take the intersection of their closure in X sigma with the divisor determined by rho. Okay, so essentially what this is some sort of combinatorial description of the leaves of this, the symplectic leaves of this foliation inside of the boundary divisors. So the boundary divisors themselves have big open tori inside of them. So what these big open tori are is just like the vanishing locus of monomial equals some constant, so the fibers of some monomial function. And so this monomial function is just determined by the data of the ray and the pairing that you started with. Okay, so this was described by Hacking and Kiel. And so if you start to do what I sort of talked about in the previous slide, that is, you take these leaves, so you take your pairing, you take your toric variety, and you start to look at these symplectic leaves in different components, and you start to blow up. So the question is, what do you get? So you can just make choices and start to blow up, and what you essentially get is every time you blow up, you add another cluster chart. So you get some variety that's up to codimension 2 covered by 2D dimensional tori. And in fact, so this is closely related to some cluster variety, and in more precisely, so if you take alpha to be the adjacency matrix of an acyclic quiver, and you take sigma to be like the standard simplex or some standard simplex cross a lattice or something like this, so something resembling a standard simplex inside of your lattice M, then what you end up producing is an acyclic cluster variety, just by this iterated blow-up process. Okay, so you recover something very close to things like cluster varieties. You can recover things like multiplicative hypertoric varieties this way, so stuff like that. Okay, great. So this is what happens when you look at the toric examples. We can also play the same type of game for the examples of Fagan and Odesky. So Pym gives a nice description of the symplectic leaves in this case. So as I said, the divisor YE is composed of two different things. So you have the resolution of the secant variety, and you have a blowup of P4 in the symmetric square of an elliptic curve E. So secant variety over an embedded elliptic curve, and P1 bundle over the symmetric square. So just to describe the symplectic leaves of these things, so let's talk a little bit about the geometry of the components. So you can take the resolution of the secant variety. So this gives a P1 bundle over the symmetric square of E. Of course, this is maybe straightforward, but to every pair of points in E, you get a line. So of course, there's a corresponding map which takes you to the symmetric square. And the exceptional bundle, again, is a P1 bundle over the symmetric square of E. So this is, again, just obvious because you're blowing up in the symmetric square. So the symmetric square of E is itself a P1 bundle over E. So you add a pair of points in here and you get the corresponding map to E, to the elliptic curve. And the fibers are just going to be P1, so the quotients of E by an involution. So this means that both components are iterated P1 bundles over an elliptic curve. And if you want to describe the symplectic leaves of these these components, these are just fibers over E. So these are ruled surfaces over P1. So that's what the fibers of this the symplectic leaves of this thing are. So then you can just sort of run the algorithm in this case. So you choose an arbitrary number of symplectic leaves in each of these components, and you start to blow up. And eventually you'll get some sort of infinite collection of topologically distinct log symplectic pairs of pure weight 1. Okay, so you can sort of just construct these things anytime you have one to start with. You can build more. So this brings up the following question, which is something that I honestly don't know how to answer. I mean, I don't even know if there is such a nice classification, but you can sort of say, so can we write down a finite number, or maybe not finite? Finite's probably the wrong word here. Like a well understood collection of families of log symplectic pairs, from which all others can be produced by this type of blow-up procedure. So this is kind of optimistic. There's in higher dimensions. In dimension 2, this is what works. In higher dimensions, there's of course subtle things that can happen in higher codimension, which means that this is probably not the right thing to think about. But I think as sort of like a course tool for constructing these things and for producing more examples, this is sort of an interesting idea. And yeah, so another thing that I should maybe remark is that the normal crossings condition is generally probably too strong for any real applications, but it's really nice when you start to compute with mixed Hodge structures. Okay, so this finishes sort of what I wanted to say about the geometry of these things. I have something to say about cohomology. I don't know, should I say that, or should I just end here? Any comments would be appreciated or accepted.
No, I'm more than happy if you want to carry on.
Okay. Yeah. Okay. So I will continue then. I mean, this might take a couple minutes, but I don't want to take up anyone's time. Okay. So this is sort of geometrically the classification. What I want to do now is I want to talk about what this pure weight condition means for the cohomology rings of log symplectic pairs of pure weight 2. So I focus on pure weight 2, not pure weight 1 or pure weight 0, because it's sort of easier to describe, mostly. But it also sort of brings up relationships between other subjects as well. So there are three main properties that you can sort of determine about the cohomology rings of log symplectic pairs of pure weight 2. These are, okay, so the first one is something that has nothing to do with pure weight or anything like this. So this is just some sort of symmetry condition. So the notation here I'm sure is impenetrable, but this basically means like, so what can I say? So this means if you think about the Hodge numbers of, or the graded pieces of the Hodge filtration on this cohomology group, this means that there's sort of a diagonal symmetry across on some axis. So this means that you have this isomorphism between two different things, and it's induced by cut product with your log symplectic form. So this is a basic thing. Okay, this is fine. A more interesting thing is the following. So we say that a mixed Hodge structure is Hodge-Tate first of all, the odd weight graded pieces all vanish, and the weight and Hodge filtrations are opposed. So this means specifically that you can identify the dimensions of the weight graded pieces with dimensions of Hodge graded pieces. Or you can say this another way by saying that that IPQs vanish unless P is equal to Q. So maybe the most down-to-earth way of saying this is that if you look at the even weight graded pieces of this cohomology ring, then well, I guess what I've written here is referring to a log symplectic pair, but regardless. So if you take the even weight graded pieces of this thing, then these are all sort of, all HPQs of these even weight graded pieces vanish except if P is equal to Q. So, think about the cohomology of a toric variety or a torus or something like this, an algebraic torus or something like that. Okay, so the simplicity result is that if you have a log symplectic pair of pure weight 2, then your entire cohomology ring is Hodge-Tate. So just to bring this back to something that I was saying before, so this is really kind of the embodiment for log symplectic pairs of the philosophy that structure of the cohomology ring is determined by the structure of H2. So if you have a log symplectic pair of pure weight 2, then what's happening, your log symplectic form is something, well, this is just something that lives in H2. So knowing where this lives in terms of the weight filtration determines the structure of the weight filtration all the way up the chain. So that's sort of the idea here. This tells you how to go from degree 2 to all degrees to get some information about that. As a corollary, and I won't explain this in detail, but this is related to if you've seen, stuff about the, cohomology of character varieties, work of Hausel, Rodriguez, and Villegas on this. So there's this property that they study called the curious hard-Lefschetz property. So this means essentially that the cohomology ring here, there's some element in this cohomology ring whose cut product acts like a relative anti-canonical class or relative ample class of a fibration on this thing. So this is this curious hard-Lefschetz property. It's related to the P equals W conjecture and stuff like this. So what we have is that the cohomology ring of log symplectic pairs have the curious hard-Lefschetz property if the symplectic form is pure weight 2. Okay. So just going back to the examples before, this actually gives a proof of something that was proved earlier by Lam and Spire, which is that if you take an acyclic cluster variety, then the cohomology ring, that thing, has the curious hard-Lefschetz property. So this recovers an older result of Lam and Spire. Okay, so as a consequence of, again, this simplicity condition, you can see that different cohomology groups of log symplectic pairs of pure weight 2 vanish. So specifically, if you take I to be your degree of the cohomology group, and this I is greater than the dimension of the variety, then your cohomology vanishes above that degree. So essentially what this is saying is that in some sense, the cohomology groups of a log symplectic pair of pure weight 2, they look like the cohomology of affine varieties. But it's also true that these are not necessarily affine. So this is a fairly strong condition, that you know, this behaves, you know, in terms of vanishing like an affine variety. Okay, so these are the main properties of the cohomology of log symplectic pairs of pure weight 2. A lot of the structural results that I've talked about here have analogs for the cohomology of degenerations of good degenerations as well. And so as an example of this, you can recover this theorem of Soldatenkov, which says that if you have a good degeneration of type 3, then the corresponding limit mixed Hodge structure is Hodge-Tate. Okay, so yeah, so this is again a simplicity condition, and this is a statement about how, you know, again, mixed Hodge structures of higher cohomology, pieces of the cohomology of these things are determined by the behavior in low degree. So saying that you're a good degeneration of type 3 means that something happens in H2, but then whatever happens in H2 is now saying there's simplicity higher up the chain. Yeah, and as I said before, there's analogs of all this for pure weight 1 things, but it's a bit more difficult to state. Okay, so that's what I had to say. Yeah.